second derivative stuff, the assignments. And we, it's been a while since we talked about this. This would be probably a good review. And you get some problems like this where you're going to try to relate the graphs of the function to the first and second derivatives. And you guys should be pretty good at this. We've done a lot like this already. So here's the function. Let's graph the first derivative. Okay, where's a point that we know on the graph of the derivative? At 0, yeah, right. At 0, what's going on?
It's horizontal.
Okay, good. Horizontal tangent. So what's that? What's the value of the derivative?
0.
0. Okay, so you know that the derivative function is going to go through there, isn't it? To the left of that, what's happening with the derivative?
It's decreasing.
Decreasing. Okay. To the right?
Decreasing.
To the right, it's also decreasing. Okay. And it's going through, it's negative on this side and negative to the right of this point also. Agreed? Okay, but it's 0 at that one point in between. So what should this probably look like then? No, now you got to remember the value of the derivative function is equal to the slope of the original function. You got some mental gymnastics you got to do there. So if it were a straight line, then what would that tell you about the derivative function? I mean, if the derivative function were a straight line, then it would be a constant negative slope. Actually, no, that's not true. It would be starting very steep in the negative direction. So here's the suggestion. You tell me why this is wrong. You guys are saying this, right? You're saying probably something like...
No, I'm just guessing.
Oh, okay. I mean, this is what I think you were saying, though, right? Was that? Okay, well, let's just take a second. Why is that not right?
Because your slopes are changing.
Yeah, this would imply if this is the graph of f prime, that would tell you that, for example, when x equaled -1, the derivative had a positive value. It didn't. Never did, right? The derivative was negative there. Okay? Ah, okay. That's going to be a parabola, isn't it? What kind of parabola? Opening up or down?
Opening down.
Opening down. Everybody see that? Because I have to have, that would make sense. Something like that, wouldn't it?
I was going to say that, but I was like, well, wait, because the slope is positive, but it's not.
That actually works though, doesn't it? Because look, we can see up here the slope is negative and decreasing. It's negative and decreasing at a decreasing rate, and it gets to 0, right? It flattens out. And then to the right of that, it's 0, it's decreasing slowly, decreasing quickly, right? So it makes sense that it would be a parabola. Now, there's another reason you might suspect that's the case. What kind of function does that look like? Looks like an x cubed function, doesn't it? It looks like a cubic, right? It's an odd function because it's got its behavior, end behavior is positive to the left and negative to the right. So we know it's an odd function. And so then the derivative is going to be an even function, isn't it? Right? A polynomial like that. Okay? So there's the first derivative. What about the second derivative? They just keep getting simpler, don't they, when we're talking about polynomials? Yeah, that's one where it's going from a positive, a large positive slope, smaller positive slope, 0, small negative, bigger negative. So that's one that starts to look like that, doesn't it? So there would be a double prime. Okay? All right, how about something like this? So consider the graph of f prime and f double prime shown to the right. On the same set of axes, sketch the graph of a possible function f. Now, there's no one right or wrong answer. right? And the reason that is because it wouldn't make any difference if I shifted these curves up and down, the slopes aren't gonna change, right? Okay, so what about this one? Now we got a bunch of information here. We wanna try to graph the original function. What's some stuff that the blue first derivative graph is telling me?
There are some flat tangent points.
Brittany, just go ahead.
The direction must be up to the fourth because the graph of.
Okay.
left kind of goes to the third.
Okay, so that's one thing we can see, sure. So the second derivative looks like it's quadratic, first derivative looks cubic, so the original function must be an x to the fourth. That's good thinking. Okay, are there some places on the blue graph that we can use to sort of pinpoint some important points on the graph of f? Okay, so for one thing, okay, here's suggestion is, how about the point right here where we have we have a horizontal tangent? Okay, the horizontal tangent, what does that correspond to on the red graph?
So you're going across.
Ah, yeah, because remember, the second derivative graphs the slope of the first derivative, right? And the first derivative graphs the slope of the original function. So it makes sense then, doesn't it, that this correlates to that point right there, doesn't it?
Yeah.
Right, because that's a place where the second derivative has a zero value. Okay? So that may end up being important to us, but that's not what we were maybe going for. Right, now what are the places, now think back to the first derivative test. What are the kinds of places on the first derivative that are interesting to us on the original function? Places where the first derivative is doing what? Zero or undefined, right? Those are the critical numbers. Okay, so let's go back a little bit then. You see some places where the first derivative is zero. Well, yeah, we got a place there, right?
Yeah.
We got a place there, and we got a place there. So if we were to split the plane up, let's divide it up vertically into some regions. So one region would be to the left and right of that zero of the first derivative. Here's another one right here, and here's another one right here. Okay, what's the sign of the first derivative to the left of this boundary? Negative. Okay, so the first derivative is negative or positive? Positive, isn't it? Right? Because the first derivative is above, it's got positive value, and once again, there's those mental gymnastics, because you're thinking about this in terms of a slope probably, right? But remember, the first derivative is the graph of the slope values, isn't it, right? So here's where the first derivative is positive valued, in here it's negative valued, in here it's positive valued, and here it's negative valued. So what does that tell you then about this critical number?
That's where yeah.
Okay, it's where the slope is going from increasing to decreasing, so that has to be a maximum, doesn't it? Okay, good, that's a maximum. Does that correlate to what you're seeing with the second derivative? Look, the value of the second derivative at this point, at this critical number, is negative, isn't it? Okay, so negative, what's that tell you? The second derivative is negative. What does that tell you about the shape of the function? Remember, second derivative was kind of weird. What did we call the
rate of change.
It's the rate of change of slope. And what was first derivative tells us slope. What do we call that? Second derivative is telling us,
Rate of change of rate.
it's a rate of change of rate of change. But what was the word we gave to that? Right? Concavity. Yeah. And if it's a negative concavity, remember what we said about that. A negative concavity means it's going to be concave down. So those are going to be regions where a tangent line sits above or below the graph. Below. Hold it. No, if it's negative concavity. It's going to be above, isn't it, right? If it's negative concavity, that would mean if an ant were, let's just step back a little bit and go back to the picture we drew for that. Where was it? So we just use this, we use Desmos, didn't we? Right, that's all right. So here's an example of a place where it's concave down, right, it's shedding water. So if I drew a tangent line, notice that the tangent is gonna be situated on top of the curve. So there's the hallmark for negative concavity. Here's a place where it appears to be kind of a section of curve that's bowl-shaped up. That's gonna tend to catch water that's falling. And so here, if you look at the tangent line sits below the curve. And so that would be upward concavity, right? Okay, so then, oops. Okay, so then if this is a place where the concavity is negative, it's bowl-shaped down, and it's got that fits, doesn't it?
Yeah.
Right, downward concavity plus horizontal tangent equals maximum, doesn't it? Right, so we know that the curve at this point is gonna have to be something like that, isn't it? Okay. What about this place right here? Okay, so this is a place where we're transitioning from negative to positive. So that should be bowl-shaped up. And sure enough, look what happens there. That's a place where the second derivative has a positive concavity, right? Which is bowl-shaped up. So that makes sense. Well, how could I link together smoothly if we're going to assume that this is a continuous function, right? If it's got to have a maximum at this value of x and a minimum at this value of x, that one has to be lower than that one, doesn't it? Right? So we're going to have a minimum there. And then if we keep playing this game, we're going to get, here's another place where we get a horizontal tangent. This time we're going from increasing to decreasing again, and you can see that the concavity is clearly going to be negative. And so we're going to get something like that again, aren't we?
Yeah.
Right? And so that makes sense. We can connect these and make a curve that does that, can't we?
Yeah.
Right? Okay, but what else is being told to me here? There's something else in this red graph that's interesting. What would the zeros of the second derivative be telling me? Like, look here. Yeah, okay, so here's a place right there where we've got a point of transition of the second derivative, right? And here's another one right there. Okay, and to the left of this, I guess we could call it a critical number, couldn't we? To the left of that critical number, we have a negative second derivative. To the right, it's positive. And then to the right of this one, it's negative again. So this is, you see that this is analogous to what we did with first derivatives. We found places where the second derivative was equal to 0, and those are in fact second derivative critical numbers, right? Those are places where we could have transitions of the concavity. What did we call a place that was a point of transition of concavity? Remember? So we had extrema, minima and maxima were points of transition of the first derivative. What was a point of transition of the second derivative?
Refractal.
No. It sounds like that,
That's
though.
what I say, it's
Yeah.
not,
It sounds like that.
it's not a referendum,
It's not a referendum, no.
it's not a recall, it's not a recall.
It was
What a
an inflection point, right? Inflection point is where we're transitioning. So we can see here, we're getting an inflection point. This is gonna be along this vertical line, that's gonna be the x value, where we're gonna transition from negative concavity to positive
but I need
concavity,
the following
right?
students
So
to
if
the
I wanted to
main
draw this a
office,
little more
please.
carefully,
Landon Thornburg,
it would have to look
Maddie
like this,
Thompson,
wouldn't it? There's gonna be
Kinley
my
McAnally,
maximum.
Bree
That's
Young,
where I'm
and
transitioning from
Mackenzie
concave down to
Henninger,
concave
and
up,
also
and there's
Kimberly
my
Peck to
minimum.
the attendance office.
Here's gonna be the point of transition of concavity again, so it's gonna move along, concave up, now it's gonna turn to concave down. And there's my function. Everybody see that?
Yeah.
Is that the one function? No, not at all. I mean, the thing could be shifted up or down vertically, and it wouldn't change any of what we talked about, okay? All right, we'll get back to this. Hopefully by then, everything will be fixed on Math Excel.